0. Okay, great. Let's try some problems to get the hang of this. So here's a graph of the electric field with respect to X. Notice the units here, volts per meter, okay, volts per meter. We had been using the electric field, right, was like a force over a charge. So it had units like newtons per coulomb, okay? But now we also see that the electric field is like a change in a voltage over a change in position, right? So it also has to have units like volts per meter. So these two collections of units, newtons per coulomb and volts per meter, are equivalent. If you break that out into their fundamental units contained inside of those different quantities, you'll find that those are identical unit sets. So we'll go back and forth and use those interchangeably depending on the problem. So I'm showing you a function of the electric field in the X direction with respect to X. And what we want to do is we want to find what the electric potential is over here. What is V here? If we know that the electric potential at 0, or the electric potential at position 0 starts at 0. So let me see what you guys think. Let's start the polling. Okay, let's go ahead and end the polling. We're trying to find the change in the potential. Our equation tells us that the change in the potential is equal to minus the integral of that electric field in the X direction dx. Right? This is the area under that E versus X curve. So I need to find this area. Well, notice that area is all above the x-axis, right? So that has positive area. So in this example, this area is going to be positive. What does that tell us about the value of the change in the potential? Well, if the area is positive and I have this negative sign sitting here, it tells me that the change in the electric potential is going to be negative. So I can see that just because I have positive area under that curve, that my change in electric potential better be negative as I move from 0 to 1. So it's got to either be D or E. Well, let's see what the magnitude or what the value of that area is, right? Well, I can see that that's just half of this rectangle that has a side like 2,000 volts per meter times 1 meter. So the area there is like 2,000 volts per meter times 1 meter divided by 2, because I'm just looking at that triangle here. That gives me 1,000 volts. So I know I have a negative 1,000 volts here. What if I did this the opposite way? What if I said we start at 1 volt, sorry, we start at position 1, and we define the voltage to be equal to 0 at 1. What would the voltage be over here at position 0? Can we redo that? Can we relaunch the poll here? See, what if I switch this around and say that the potential is 0 at x equals 1 meter. What is the potential at 0 meters? What would it be? Okay, let's go ahead and end the poll. So many of you said 1,000 volts. That's right. The voltage has to be 1,000 volts here. I know that I lose, right, as I move in this direction, I know that I lose 1,000 volts because that area under that curve is positive as I go from 0 to 1. Okay. So, right, if I'm going backwards from 1 to 0, right, what happens as I do that? When I write this integral, it would be like I would start at 1 meter and I would want to end up at 0 meters. Well, remember what you have to do in an integral when you have the smaller value on top. You have to flip those limits of integration, and that's going to put a negative sign, right? That's equal to positive the integral from 0 meters to 1 meter of dEx dx. This is exactly the area we calculated before. It was a positive 1,000 volts, and now I have a positive sign sitting out there because of the limits of integration that I have here. In both cases, right, the voltage at one meter is 1,000 volts less than the voltage at 0 meters, and that's the key thing. This equation only tells you about changes in voltage, not the absolute voltage at any point. Okay? That absolute voltage, or the initial conditions of some voltage, are actually just free choices, right? We can define those initial voltages however we want. If the problem defines it, use their definition. Otherwise, you're free to define your point of 0 voltage as you choose in the problem. In just the same way as we're free to define the points of 0 potential energy when we were doing gravitational problems. What about this one? Now we have a graph of potential as a function of x. And I want to say something about the electric field. So we need to be able to understand the electric field from a function of potential. And so we're going to have to use this functional form that the electric field is minus the derivative of the velocity function with respect to x. So at which point, xa or xb, is the electric field stronger? Where is the electric field stronger? Okay, I'm gonna give you guys 2 more seconds. Let's end the poll. All right, so most of you think that the electric potential is stronger at position A. Okay. Well, this we know is just the slope of that potential versus position function. So here at B, right, the slope is gonna be this line, right? It's the slope of the line that's tangential to that curve. Over here, it's gonna be like this. So this is steeper, right? And this is more shallow. So the steeper, right, the larger slope has the, right, the steeper slope has the larger magnitude for the derivative. And so we can see that position A has the larger slope, has the stronger electric field. Is the electric field negative or positive in this example? Is it a positive electric field at XA or a negative electric field? What direction does the electric field point? What do people think? Okay, some negative, some positive coming in on the chat. Well, look, the slope we just said is positive. We see that. But the electric field is minus the value of the slope. So the electric field at XA is less than 0. It's negative. So what does that mean? A negative electric field means the electric field is going to be pointing towards values of decreasing x, right? So at this point, the x direction of the electric field there points back towards the left. Right, and that's what we might expect because we know particles want to move, right, positive, right? If I had a positive particle and I put it in this potential, it wants to move towards decreasing values of electric potential. Okay, what about this one? So now we have an electric potential that I show you in the plot at the bottom here. And we're gonna imagine that we put a charged particle, a negatively charged electron, into this space. And we're going to put it right here at 2 meters. And then we place it there at rest, and then we're going to release it. And we want to know what happens to that electron right after I release it. Okay, so it's going to start moving, or it's going to stay put. Which one of these describes the motion of that electron after I release it? Okay, still see some votes are outstanding. Let me give you about 10 more seconds on this one. Okay. So let's see if we can reason through this. Well, we're trying to describe something about the speed and the direction that the particle starts moving. So that means it starts from rest. We know that the initial velocity is equal to 0. And we want to know something about the final velocity and how it's evolving. Right? So we're trying to find some information out about a change in how the velocity is changing. I'm going to try to use a script V if I'm representing velocity so we don't get confused with the voltage. Well, what leads to a change in velocity? This implies that there has to be some acceleration acting on the particle. And where does an acceleration come from? Well, an acceleration means there has to be a force acting on the particle. And for a charged particle, it experiences a force by interacting with an electric field, right? Q times E. Now I can get the electric field from a change in the electric potential, right? I know that the electric field is equal to minus dV dx. And then I can just chase this relationship through, right? So what does this say? I can see from the plot that the slope, right? This again is the slope. The slope is negative in this example at position 2 meters. That means, oops, excuse me. That means that the electric field, right, has got to be positive, right? The electric field is got to be greater than 0. I have a negative slope with a negative sign in front of it, means I'm going to have a positive value for the electric field. So the electric field points in this direction. What direction does the force point? Well, I can go to this equation. Once I know the electric field, the force points in the direction of the electric field, but with this charge sitting in front of it. This one has a negative charge, so I can see the negative charge hooking up with the positive electric field, that the force is going to point in the opposite direction of the electric field for this negatively charged object. So because I have an electron, the force is going to oppose the electric field. And now I can see that implies then that there's a change in that if there's a force, I know that the force is also equal to ma. So the acceleration is aligned with the force, points in that direction. Okay. So I have an acceleration back to the left. So that means the particle is going to start moving to the left, right? So it's got to be one of those. But because it's accelerating, it's got to be doing it with increasing speed, not steady speed. Otherwise, I would have no acceleration. So this particle is going to move to the left with increasing speed by chasing through that whole relationship, right? From the potential, we can get the electric field. From the electric field, we can understand the force. Once we have the force, we can understand the acceleration. So we should be able to look at plots like this. Again, here I'm showing voltage as a function of position. And we should be able to graph the electric field as a function of x across this whole region in space. So let's see if we can do that together. Let me get my notepad here. Okay, so let's try to draw a graph of the electric field. Let me get black here. The electric field with respect to x. Let me draw this out here. Something like this. So let's go bit by bit here. Let's start with some regions that might be easier. Let's start with this region between 2 and 4. What's the electric field in this region between 2 and 4? Can somebody tell me the electric field there? Put what you think the electric field is in that region in the chat. Remember, we were given the potential, so if I want the electric field, it's minus the derivative of that potential with respect to x. That's how we're going to turn that graph right into this graph. Okay, I'm getting a bunch of zeros, right? That's correct, right? Why? Because between 2 and 4, this function is flat, so dv dx is equal to 0. There's no slope. If dvx is equal to 0, that means this thing is just going to be equal to 0. It's just going to be flat between these two. What about from 4 to 6? What about from 4 to 6? Can somebody describe, or can you guys all try to type in to the chat how you think the electric field looks between 4 and 6? How about let's start with the sign. What's the sign of the electric field between 4 and 6? Is it positive or negative? Okay, good. I'm getting positives coming in. Why is that? I see that I have a negative slope. Right? Slope is less than 0. If I have a negative slope, because I have this minus sign in front, it means I'm going to end up with a positive electric field. I can find the magnitude of that electric field then by, right, finding that slope. Well, here I see that the voltage changes by, right, so that slope is going to be the, since it's just a flat line, is going to be the change in the voltage over the change in position. Well, I can see that that I change by 20 volts as I move 2 centimeters. I drop by, right, I drop by 20 volts as I choose. So the 2's are gonna cancel out and I have a minus, so I'm gonna end up with something that's like minus 1,000 volts per meter. Okay. So over here, I'm gonna end up with something up here that's again positive 1,000 volts per meter. What about between 0 and 2? What's happening? Is the electric field positive or negative between 0 and 2? What's happening to the sign of the electric field between 0 and 2 centimeters? Is it positive or negative? What do people think? Okay, negative, right? I see everywhere here that the slope is negative. Now it's not going to be constant because I see the slope is varying, right? Down here close to 0, I have a very flat slope. So the electric field should be 0 or close to 0. And then that slope is growing more negative as I go up to 2 meters. So it's linearly increasing because right, you can imagine this is a parabolic function. So maybe say it's something like x squared. It's going to have a linear behavior. When I take the derivative of that parabolic shape, it's going to have a linear decrease to it. What's the value that it's going to end up here? Well, I could try to figure that out, right? Look at this, draw a line tangential to the curve, try to figure out that slope. You can convince yourself here that for 1 centimeter, I don't know, maybe it changes by 20 volts in that 1 centimeter there. So you could try to estimate the slope from this graph. So maybe it ends up here at sort of twice the steepness, or like minus 2,000, something like that over here. If we wanted to get the exact value, right, we would need the functional form for that parabola, and we could do the derivative of that, calculate the derivative and evaluate it at that specific function, at that specific point. Okay, questions about that? What about this one? Now I have a plot of the electric field as a function of x. So you can see it's 0, and then it's got these discrete kind of regions where it's uniform. Can we make a plot of the electric potential as we move along in x if we assume, right? So remember, we said that we always have to, right, because how are we going to do this? We know that the change in the potential is going to be equal to minus the integral from, say, some next x position to some final x position of ex dx, okay? And all this tells us about is the change in V. So that means we always have to define an initial voltage somewhere in the problem. So they give that to us in this problem. They say, we're going to define that voltage is equal to 0 at the origin here. Okay. So let's try to plot the electric potential for this function. Okay. Again, we're going to have, we want the voltage as a function of x, and we're going to divide it up into these different regions here, 2, 4, 6 centimeters. Okay, let's look at a few different regions. Well, here we see things are constant from 0 to 1 centimeter. What's the change in the voltage? So first of all, okay, let's put one thing. They tell us that voltage is equal to 0 at position 0. So we can just pin that down on the graph. How does the voltage change as I go from 0 to 1 centimeter? How does the voltage change? What do people think? How does the voltage change? Well, I can look over here. I see this integral, and I know this is the area under the curve, under the E versus X curve. Well, here I can see, because I'm sitting at 0, there's no area under this curve, so the change in potential has to be 0. So that means over this region, I have no change in the electric potential. And then I see as I move from 1 centimeter to 3 centimeters between this region, well, now I end up with, right, some electric field sitting there. What's the value of the electric potential going to be when I get to 3 centimeters? Well, how am I going to find that? I would have to integrate this curve. Okay. When I get to 3 centimeters, is the voltage going to be positive or negative? What do people think? Let's put in our answers in the chat. Is the voltage positive or negative when I get over here at 3 centimeters? voltage is going to be negative. I see a lot of negatives. Does everybody agree with that? Well, let's see. Is the area under this curve positive or negative? The area there is negative, right? It's below the x-axis. So the area is less than 0. But remember, there's a minus sign for the delta V. So the area is negative, but that implies that the change in potential is positive. So the potential has to increase. Okay? So the potential has to go from 0 to some positive value. And at 3 centimeters, it's going to be that area under the curve. What is that going to be? That's going to be my 2 centimeters times this minus 200 meters, right? So that's going to be 200 volts per meter, right? So that area is going to be 200 volts per meter times 2 times 10 to the minus 2 meters. That's 1 over 100. That's going to cancel out here. And I end up with something that's like 4 volts. Okay. This thing has to increase by 4 volts. So when it gets out here, it's going to be 4 volts. What do we think the potential is at 2 centimeters? So we see that over here at 3 centimeters, it's got to be 4 volts. What's the voltage at 2 centimeters? What do people think? Well, let's see if I want to get the change in voltage. Oops. If I want to get the change in voltage to 2 meters, well, now I've only gone this far. So look, I have half the area under the curve between 0 and 2. That means my voltage has changed by half as much. So it's here at 2 volts. Right? And I'm just getting this linear increase as I go from 1 to 3. Now from 3 to 4, again, we see over here that I have no electric field, so there's no area under the curve, so I just have no change in the potential. That doesn't mean my potential goes back to 0. That means my potential doesn't change between 3 and 4. Right? Delta V is equal to 0. If it dropped back down to 0, I would have a large change in potential, so I would get an electric field. So what it means is whatever the value of the potential was at 3, it stays that all the way until 4. And then what happens between 4 and 6? Well, between 4 and 6, we can see I've got this positive area. That means I'm going to have negative a change in voltage, right? I'm going to be losing voltage. And so this thing is going to ramp back down, right? It's that same area, so it ramps back down to 0. So we get something like this. The voltage is 0 between 0 and 1, increasing linearly as I go to 1 and 3, then maintaining a constant value as I go from 3 to 4, and then linearly decreasing as I go to 6 centimeters. And you can check, now you should be able to go backwards, right? We see there's a constant slope here. And that if I calculated that constant slope, I see that it's negative, and I know that the electric field is equal to minus dV dx. I've got a negative slope, so that means I would have a positive and constant voltage, right? I can check that graph that I made, make sure when I take the derivatives over those different areas that I can get back the electric field that I see on the left-hand panel here. How would I create a field like this in real life? What kind of devices would I need to create an electric field that looks like this? That's 0 and then negative and then 0 and then constant positive and then 0. Any ideas? If you have an idea, go ahead and raise your hand and you can tell us what you think. How would I build a device or a set of devices that would create this kind of electric field? No ideas? Well, what kind of electric fields do I have in these regions of space? This is a uniform electric field. What kind of devices create uniform electric fields? Have we seen any devices that generate a uniform electric field? Devin on chat is saying a capacitor. It's exactly right. It's a capacitor generates a uniform electric field. So how many capacitors would I need to create this kind of electric field? Well, where is the field uniform in a capacitor? Between the capacitive plates, right? So how many regions of uniform electric field do I have here? I have 2 regions of uniform electric field. Remember, everywhere outside of the capacitor in an ideal case, yeah, Nathan is saying we need 2 different capacitors. What would they have to look like? Well, I could configure something like this. I could have a set of parallel plate capacitors like this. Here I see the electric field is negative, so it should point towards decreasing values of X. So if I had a positively charged plate here and a negatively charged plate here, I would have electric field that pointed back like this, right? I would have a negative value of electric field. And then in this region in space, I could have a positive plate here and a negative plate here and create electric field that points back to the right. And everywhere else, the electric field would be 0, everywhere outside of the capacitor in the ideal case. Right? So with 2 capacitors, right, with the right amount of charge built up on the plates, I could generate an electric field that looks like this in space. Okay. All right, this is the last problem for today. So I have now a visualization of the electric field that exists in some region in space. It's uniform and it kind of points up to the right, as you see here on this slide. And I'm imagining 2 points, position 1 and position 2. I want to know which point, let's say that there's a potential here, V1, and there's a potential here, V2. Which point is higher, has the higher potential, V1 or V2? Let's put some answers here. Let's say A and B and do a poll on this one. Their choices are A or B right now. So do you think point 1 or point 2 has the higher potential? Okay, I'm going to go ahead and stop the poll. Most of you picked that point 1 has the higher potential. That's right. Remember we said earlier that the electric field points towards lower potentials. E, right? We can see that from the equation. E, say S, is equal to minus ds dx, right? So the electric field, the positive sense, right? The electric field is going to point, right? If this guy is negative, dV is negative, then the electric field, right? If I move in the sense, right? If I move in the direction where delta V is negative, then it tells me that the electric field points in the opposite direction. Or sorry, no, it tells me that the electric field points in that direction, right? If dV is negative, if I move in the direction that I find decreasing values of electric potential, it tells me that the electric field is aligned with that direction. Okay? So the simple thing we say is that the electric field points from high potential to low potential. So in this case, V1 has got to be greater than V2. Okay. Can we find this, the delta V? Can we find V2 minus V1, that delta V? Well, how am I going to do that? I could calculate that in this curve. Remember, delta V, the change in the potential, is equal to minus the integral of ES ds, where S is this direction that points in the direction that I travel, right? I go from, say, S1, position 1 to position 2. Okay. So this is my S direction. Well, in this particular example, this integral is pretty trivial. Why? Because the electric field I see is uniform everywhere along that direction. And so I can pull ES out. And this is integral of S1, S2, ds. And so this thing is just going to be minus ES delta S. Oops, delta S. And I know both of these things. They gave me the magnitude of the electric field that points in the S direction. Look, it's all aligned already with the X direction. I don't have to pull out the component. And I already know what delta S is. It's 10 centimeters. So if I want to know what the potential is, the change in the potential is going to be equal to minus 200 newtons per coulomb. That's also the same units as volts per meter. So I'm going to change it to volts per meter, because then I'm going to multiply this by 10 times 10 to the minus 2 meters. And I can see the meters cancel out to give me something in units of volts that's like, what is this going to be? 100 cancels out here. It's going to be like minus 20 volts. So I can see the change in the potential. I lose 20 volts as I go from 1 to 2. What about this last one? Can we draw the equal potential surfaces? Can we draw the equal potential surfaces? Well, we're free to choose this initial potential. So let's say that the potential 1 is equal to 0. Well, I know then that everywhere in this position, first of all, we know the electric field is perpendicular to the equal potential lines. So I know those equal potential lines, there's one potential, that equal potential line has to follow this path so that those electric fields are perpendicular to it. Now, how far do I have to travel in space to change my voltage by 5 volts? Well, we saw that I had to travel 10 centimeters to change things by 20 volts. 5 volts is a quarter of 20, so I have to travel a quarter of the distance, right? 10 divided by 4 through this thing to find these equal potential lines. Right? So the equal potential surfaces look something like that. If I start with 0 volts, then this is going to be minus 5 volts, minus 10 volts along this line, minus 15 volts along this line, and ending up with my minus 20 volts over here. Now this initial condition from the voltage was a free choice, right? We could have also said that the voltage here at 1 was equal to, say, 60 volts. That's something we get to define. But then what happens is I go to these equal potential surfaces, the change in the voltage has to be the same as what we saw before. So this guy would have to be 55 volts, this guy would have to be 50 volts, this guy would have to be 45 volts, and this guy would have to be defined as 40 volts, right? So I still have a drop, right? The physical thing is that I see that there's a drop in the electric potential of 20 volts as I go from that initial position to that final position. Okay, guys, we're gonna go ahead and stop there for today. We'll pick up here tomorrow. If you have any lingering questions, I'll stick around for a few minutes to answer them. And then otherwise, I will see everybody tomorrow. Thanks so much. Have a good day. Bye, guys.